My name is Nurdia Kamalia binti Hamidun. My matrix number is 196323.
Hi, my name is Nur Aini Sofia binti Hashimti and my matrix number is 198442.
My name is Nur Imanina binti Muhammad Haiza. My matrix number is 198420.
Hi, my name is Nur Najiha binti Zainal and my matrix number is 198780.
Hi, my name is Nabila binti Mahmud Seri Wijaya. My matric number is 197817.
Let's start with the meaning of equilibrium. Equilibrium is a static condition in which no changes occur in the macroscopic properties of a system with time. You must be wondering, what is the meaning of macroscopic properties? Macroscopic properties is a characteristic or behavior of a sample that is large enough to see, handle, manipulate, and weight. For example, pressure, volume, temperature, composition, and density. These properties consist of large number of particles. Next, a system is said to be in equilibrium when forward and reverse reaction proceed at equal rates. Apparently, equilibrium can only be happen in reversible reaction at closed system. This is because only reversible reaction has forward and reverse reaction. I will give you an easy example so you can understand more about equilibrium. Imagine that you dig a hole and at the same time your friend fill back the hole with soil. If you dig faster than your friend, the hole will become much bigger. But if your friend is filling the hole much faster than you, then the hole will become much smaller. But in this situation, if you and your friend work at the same speed, then the size of the hole will not change. This is what we call as equilibrium. Equilibrium usually appeared as coexisting phases. Here shows the most common phases that we usually encountered in life. The first one is liquid-vapor equilibrium. The example of this equilibrium is boiling water. When you boil water, you can see some of the liquid water change into vapor. The next one is solid-liquid equilibrium. One of the example is when ice water melts into a liquid water. The last one is solid vapor equilibrium, which happens when solid iodine is left in a closed jar. After a few minutes, we can see that the jar is full with violet colored vapor, and the intensity of the color increases with time. But in this video, we are going to show you what is solid-liquid equilibrium, SLE. This is one of easy example on application of solid-liquid equilibrium, SLE. Imagine that you have the same mass of ice and water in a closed system and have insulator around it. At equilibrium, which has constant temperature, the liquid water molecules attracted to ice water molecules, which usually called as condensation process. And at the same time, few molecules of ice water escape into liquid water. This is what we usually call as reversible reaction, and equilibrium can be achieved in this kind of reaction. This ice and water system will reach equilibrium at temperature 0 degrees C, which also called as melting point, where solid and liquid coexist at 1 atm pressure. Also, at this temperature, the mass of ice and water do not change with time because the conversion of solid to liquid is the same with the rate of conversion of liquid to solid.
So now, I will show you the solid-liquid equilibrium diagram or SLE diagram. The SLE diagram is a diagram of temperature against composition. Okay, the composition is denoted as X and Z, where X is the liquid phase mole fraction and Z is a solid phase mole fraction. The temperature at y-axis can be in Kelvin or Celsius. In the SLE diagram, it will have solidus line, where this line is separating the field of solid from liquid and solid, and the temperature at this line is known as TE, which is eutectic temperature. Next, we also will have liquidus curve, where the line is separating field of all liquid from liquid and solid. We will have two components in this mixture, which we denoted as A and B. Then we have eutectic point, where it is located at here, where there is intersection between liquidus curve and solidus line. Eutectic point is the lowest melting point of mixture component. The temperature remains constant at this point until one of the phase disappears, since the energy from heating and cooling is used to break down or link the bond of the molecules together. At here, we will have mixture of liquid A and liquid B. Here, we have mixture of solid A and liquid B, while here, we will have mixture of solid B and liquid A. And at the bottom here, under the solidus line, we will have mixture of solid A and solid B. Okay, now at this phase, where I denoted as A, it is the phase where all the mixture are in liquid form. As it is going down and reach at B point, it will start to form a solid A. As it's going down to C, it will be the mixture of solid A and liquid B. And as it going further down here, which I denoted as D, it will be the solid B will start to form at this point. And as it furthering down, where I denoted as E, at here, all the mixture in solid form. However, if the mixture has the specific composition where it is directly moved to this eutectic point, it will not have the combination of solid and liquid phase. The mixture will directly become solid if it has reached the eutectic temperature. So, that is all for solid-liquid equilibrium diagram.
Okay, now we will continue on how to read the solid-liquid equilibrium phase diagram and do some simple calculations. So this is the solid-liquid equilibrium phase diagram, same like the previous diagram. The horizontal axis here show the mole fraction of B, which increase in the right direction. Okay, at this point A, when being cooled down or undergo cooling process until point C and point D, which point C and point D have the same composition of mixture, which is solid A and liquid B. But when we compare between point D and point D have higher concentration of B compared to point C, since the concentration of B increase in the right direction. Then, if it continues cooling down until here, I label it as point E. This is the point of eutectic and solid A has formed. So if you want to know how much solid A has formed at this point, we can do some simple calculations. First, we label here the distance here as M and the distance here as N. In order to calculate for solid A, we take the distance of M divided by total distance, which is m plus n. While for eutectic, we take the distance n divided by total distance m plus n. The eutectic point is the point for solid-solid equilibrium, which means solid A and solid B at equilibrium. Here is the eutectic point. We can see here at this eutectic point, 35% of the mixture is solid B and another 65% is solid A. There is no liquid anymore in this phase, only solid. Okay, now let's proceed with few simple questions. First, at 350 Kelvin and 30% of it is B, what is the phase in this condition? So, at temperature 350 Kelvin and 0.3 B, the answer is mixture of liquid A and liquid B. Okay, next, what is the phase when the temperature is 250 Kelvin and 70% of it is B? So, the answer for this question is the mixture of solid B and liquid A. Now, some of us might think at this point, how much is the composition of each phase? So, this is how we can calculate it. First, we label the distance as P and Q. So, the fraction of solid B is equals to Q over the total distance, which is P plus Q, which brings 0.35 divided by 0.65, and the answer is 5385. And for fraction of liquid A is equals to distance of P divided by P plus Q, which is 0.3 divided by 0.65, which brings answer of 0.4615. When we add both of these values together, it will get total of 1. So, that is when we know the answer is correct. Happy trying!
Application of solid-liquid equilibrium in food industry. Solid-liquid equilibrium are applied in chocolate making process to prevent a defect called fat bloom, where the fat liquid in the chocolate migrate or move to the surface of the chocolate. It will resulting to a whitish and brittle appearance. To prevent fat bloom, a substance called monoterpene are mixed together with the fat. The researchers has used the solid-liquid equilibrium theory and diagram to comprehend how monoterpene can affect the crystalline behavior of solid phase of fat. This is possible because SLE diagram characterizes the solubility of a compound in a mixture or the behavior of its crystallization in the mixture. When a monoterpene is added in a fatty system of cocoa butter, crystalline habit of the diacylglycerol is altered. Solid solution will be formed and then the melting temperature of the fat increase. In a nutshell, a solid-liquid equilibrium diagram can be used to evaluate the effect of adding compounds in a food formulation.